Well, welcome to this video about making a hypothesis test with one mean value. And it's called one sample test because we have some mean value we test against some given value. So I will start with a test, show how it's done, and then I will talk about theory, about when to and not to reject H0 hypothesis. There are these four general steps in doing hypothesis testing. Step one is stating null and alternative hypothesis, and we did it in another video, and this video is about the other steps, calculating some statistic, test statistic, and converting it to a p-value, which we use to make a conclusion about whether to reject or accept null hypothesis. So the example is, let's say we have a local car dealer who is a part of some nationwide chain. And this chain has a requirement that the car sold at every dealer should have mileage less than 80,000 kilometers, no more than 80,000 kilometers. And in order to check that, car dealer has collected a random sample of 44 cars sold last few years, and we want to kind of answer the question, does the car dealer fulfill the requirement? And if we convert it to a hypothesis problem, it would be like test at 5% significance level if the car dealer fulfills the requirement. Now I say test at 5% significance level because at the basic statistics courses you usually are given some significance level, which we'll talk about later after the example. So here comes how would I do it practically. And so let's just start some text file. Let's say we have this problem. I just wrote it in a text file. Test at 5% significance level if a car dealer fulfills the requirement. So we use a t-test, and again we'll talk about why it's a t-test later on, but it's because population standard deviation is unknown, and we state this hypothesis as a first step. If you want to think about these hypotheses, you can pause the video and state hypothesis in your head on a piece of paper. But if we move on, the hypothesis would be alternative, the average mileage of sold cars at the car dealer is less than 80,000 kilometers. And alternative, we have to prove. And alternative is the reflection of the problem here, less than 80,000 kilometers. 0 is the status quo, or the opposite of the alternative, that is, it's not different from 80,000 or even more. So now it comes a little video, do it in STATA, and afterwards you insert it in this text file, the result. So after I have inserted the results, it looks like this from STATA. It's the output from STATA software. So different softwares, of course, presented in a different way, but here usually you get all three possible hypothesis tests made. Doesn't matter now what we get, we get statistic, and we also get a p-value here under each alternative hypothesis. So which one is our, and this is why it's a good idea always to state hypothesis first. Well, we tested if average mileage is below 80,000 kilometers. And we get and it corresponds to this one, p-value of around 4% or 0.04. So the conclusion would be that the p-value for the test is 0.04 and is less than the significance level of 5%. Therefore, we reject H0 and prove H alternative, that the average mileage of actually all sold cars by the car dealer is below 80,000 kilometers. Thus, the car dealer fulfills the requirements set by the chain. Basically, this is our conclusion. Here comes some theory about hypothesis test, and we can actually test three different types of hypotheses. In the case of this mileage example, we could have tested if the average mileage is different from 80,000 kilometers. Is it less than 80,000 kilometers that we actually did, or is it above 80,000 kilometers? Of course, only one is the one that actually fits the question that we want to answer. And now I'll talk about, well, you can make two types of tests, z-test and a t-test. And those chapters, they correspond to chapters in the Bowerman book of Essentials of Business Statistics. Anyway, but every statistical book or basic statistical book starts about with a z-test and then goes on to a t-test. And the idea is here that z-test is maybe easier to explain than a t-test, or I don't know why, but the problem is z-test only applies when the true standard deviation of population is known, and well, in real life it almost never is known. Anyway, but I will illustrate this hypothesis testing and talk about it using z-test, and afterwards a bit how a t-test is different from a z-test. Basically, the difference is probability distribution function. So what we calculate when we making a hypothesis test with one mean value, it's some test statistics. Let's say a z-test statistic. And this is the statistic value where we have sample mean, and M0 here is, or mu in Greek, is a population mean value assuming H0 is true. And here we have true standard deviation sigma divided by this sample square root of this sample size. So basically this is a z-statistic that we calculate based on a sample values, and we use it to evaluate if we should reject or accept null hypothesis. Let's take another example, waiting time in line. Let's say a fast food restaurant manager wants to determine if the waiting time to place an order has become longer since last month. And the question of interest is the current time longer than the last month average of 4.6 minutes? We want to prove that the time came longer, so alternative is the average is above 4.6 minutes, and H0 is, there is no change with status quo, M is less or equal to 4.6 minutes. And if you use this equation from before to kind of calculate the z-statistic, we just insert the given values into this equation here, and we get a z-statistic of 2.5. And we use this statistic 2.5 to kind of evaluate our hypothesis. Should we reject H null hypothesis and prove alternative, or should we accept null hypothesis? So in order to do that, we have to know about probability distribution of a z-statistic. And it follows from central limit theorem. Again, you can read about it, chapter 7.2 from Bowerman book if you want to know more about sampling distribution and central limit theorem. So in order to use with z-statistics to reject or to accept null hypothesis and thus to prove or not to prove the alternative hypothesis, we have to know something about the probability distribution of z-statistic. And z-statistic follows normal distribution because it is assumed that sample mean follows normal distribution, not the distribution itself of the sample, but all possible kind of samples from this population in this time, waiting time in line. Sampling distribution is normal. And when we calculate the difference between this sample value and some hypothetical value, we get that z-statistic actually follows a standard normal distribution when the H or null hypothesis is actually true. In this case, null hypothesis that mean value is equal to 4.6 minutes. It was this example with the waiting time in line. So this is the probability distribution of our z-statistic. And how do we use this information? Well, the question of interest was, is the current time longer than the past time of 4.6 minutes? And the null hypothesis is that mu is not different from 4.6, it's equal to 4.6 or less. And alternative was it was more than 4.6. And of course, which claim is true? Which hypothesis is true? This is what we want to test. And so we calculated this statistic at the beginning already, and it was equal to 2.5 with the statistic. And if we plot it in this graph, we see that it's to the right of this our zero value. And the question is, of course, this difference between 5.1 minutes and 4.6 minutes that we have calculated. Is this difference large enough to say that actually the time in line has increased? So basically, we want to say something about, is this 2.5 is actually large enough from zero that we are certain that the timeline has increased. And in this case, we need some threshold because we do not know if H0 or H alternative is actually, which one claim is correct. There is a lot of uncertainty. So we must be certain when we use this 2.5 z-statistics, we must be certain that we actually reject H0 or null hypothesis on a correct basis. There is always a risk of rejecting a true claim, in this case a risk of rejecting the correct null hypothesis that the waiting time in line didn't actually increase. So important concept here is significance level. Probability to reject true claim is called, in this case null hypothesis is called significance level, or in statistics called probability of making type 1 error, or in plain words probability of making wrong conclusion when we reject true null hypothesis. So in basic statistics, usually you given this level of significance, this threshold is 5. And also we use this 5% in the example with car dealer. And 5% marks a threshold value when we are certain that the sample mean value that we observe is actually significantly different from some hypothetical value in null hypothesis. So if we find the critical z-value is the value that corresponds to 5% significance level, the z-value is equal to 1.645. And if we depict this in this normal distribution function, we see that this point of 1.645, it is a cutoff point for a rejection region, and if our z-statistics from hypothesis test falls in this rejection region, we reject null hypothesis. The z-statistic of our test was 2.5, so it falls in this rejection region, and we reject null hypothesis, meaning that H alternative is proven, that the waiting time in line actually has increased since the last month. An alternative way of using z-statistic against some critical value is to look at the p-value. And p-value answers the question, what is the probability of sample result that we observe, in this case 5.1 minutes in waiting time in line, if null hypothesis is actually true. And p-values, they are found from probability distribution function, and you maybe already done some exercises where you given some z-statistic, you had to find probability of some event. When you have calculated z-statistic, it can easily be transformed to a probability value, p-value in this case. I will not talk how to do that. Usually software does it for you automatically. So interpretation of p-value. The p-value is used to measure the weight of the evidence against the null hypothesis. So smaller and smaller p-values provide stronger and stronger evidence against null hypothesis. And very small p-value means very strong evidence against null hypothesis. So you can focus on p-values actually from now on when you're doing hypothesis tests, because a nice thing about p-values is that no matter if you have a z distribution, t distribution, chi-square distribution, f distribution, or whatever distribution in some test, p-value will always have the same interpretation. So how do you use p-value? If you have the level of significance, you can compare your p-value, that is probability of actually rejecting a righteous or true null hypothesis, compare that value to the significance level. So you have some threshold, alpha significance level, you set it by yourself, usually 10, 5, or 1%. In basic statistics books, it's usually 5%. And if you get a p-value, let's say 0.27 or 27%, and you compare to a 5% significance level, in this case, by the rule here, you have to accept H0, and you cannot prove H alternative. On the other hand, let's say you get a p-value of 0.001, and you have set your alpha significance level at 0.01 level or 1% level. In this case, p-value is less than your significance level, and you reject null hypothesis. If you want to prove your alternative hypothesis, you want to have p-value as small as possible. So you can reject null hypothesis and prove alternative hypothesis. So in our example, what is the p-value? And if we convert z-statistic, which was 2.5, to a p-value, that is the area under the standard normal distribution to the right of the 2.5 z-statistic, you get a p-value of 0.06, or equivalent of 0.6%. So this area corresponds to this part here. This part here is p-value. So p-value is very, very small, much less than 5% significance level. Thus, we reject null hypothesis. So the waiting time in line actually has increased since the last months. So summary on one sample z-test. you state your hypothesis, then you calculate a z-statistic if it's this z-test, and convert it to a p-value, and then write a conclusion. The part that you have to focus on, of course, is stating hypothesis and writing a right conclusion. To calculate some statistic and to calculate p-value, it is actually done automatically by software. So it was a z-test, and every statistical book uses a z-test to explain about one sample test for some mean value. Now, assumption for a z-test is that you know population standard deviation. And usually you never know that if you work with samples, you only know sample standard deviation. You don't know true standard deviation. So in that case, you need to use t-distribution. T-distribution is just another continuous probability distribution, and it takes care of this extra uncertainty built in the hypothesis test when you don't know true population standard deviation but have to use sample standard deviation, which is less precise than standard deviation of population. And t-statistics looks like z-statistic. When you calculate that, the only difference is this standard deviation of sample. And this whole part is called standard error. So when you make calculations, software usually present also the statistics standard error. So it's a t-statistics. It follows a t-distribution that have n-1 degrees of freedom. And n-1 degrees of freedom means actually that the sample size suddenly matters. So when you use decision rule to reject null hypothesis based on some t-statistics compared to some critical value, then you have to find the right critical value in the t-distribution given the right number of degrees of freedom. But if you use p-value, well, we're not concerned about this finding the right critical value in the t-distribution. We just find p-value with the software and compare to a significance level. Let's do a slightly different example with car dealer. And the situation is the same. We have a car dealer that sells used cars, and now we want to test at 5% significance level that the average mileage of sold cars is 80,000 kilometers. First thing here is to state null hypothesis and alternative hypothesis. And we have three options in this case, which one is the right one. So if you look at this hypothesis test here, we have a situation where we want to test if the average mileage of sold cars is 80,000 kilometers. And it's not about something bigger or smaller, it's about something equal or different from, in this case, 80,000 kilometers. And there's only one hypothesis that you can state here. It's null hypothesis equal 80,000 kilometers and alternative hypothesis different from. And you actually don't have to make a new calculation, because as before, software presents all three options for hypothesis test, and you have here again alternative hypothesis when you have tested before less than 80,000 kilometers, and here in the middle you have hypothesis, alternative hypothesis, it's different from 80,000. So, and this p-value here I want to use to decide whether I reject or accept null hypothesis. And decision rule was as before. I showed you decision rule is always if p-value is less than significance level, you reject null hypothesis. P-value above significance level, then you accept null hypothesis. So in this case, we have p-value of 0.08, and it's greater than the given significance level of 0.05. Therefore, we accept null hypothesis, or we cannot reject it. So the average mileage of sold cars is equal to 80,000 kilometers. At 5% significance level, we could not reject this claim. So we must believe that it's no different from 80,000 kilometers. And the question is, the last question that I will end this video with, the last question is, would your conclusion change if the given significance level was 10%? Think about that. See you another time.